Hello, good afternoon. My name is Juan Alberto, and I'm doing my second teach back on connectionism, which is parallel distributed processing. And basically, what it is the shift from simple base accounts of the mind to a more a statistical approach, and it looks at the architecture of the brain, explains intellectual abilities using neural networks, which they are parallel. These networks are little brains composed of a large number of units with weights that measure the strength of connection between units. And neural network is segregated into three classes, which is our input units, output units, and hidden units. And here's a small video that explains it into more detail.
Starts with building small artificial neural networks. The individual parts here are not neurons, but units. In such a simple network, there is a layer of input units that can be compared with the light-sensitive cells in our retina. Input in these units is first forwarded to an intermediate or hidden layer, and then to an output layer. This is not only done in a serial, but also in a parallel way. The connections between the units have certain strengths that are all called weights. For example, input unit A can send a stronger signal to hidden unit B than to hidden unit C. Initially, we will have a new network that still needs to be programmed. So those weights are set randomly. An example of such a network is a face recognition network that receives photos of faces as input. It must then indicate whether or not it is a face and whether it is a man or a woman. The input layer is now not a row of units, but a two-dimensional input layer, which, for example, receives the gray values of the photo's pixels as input. Suppose we have two units as output, and we want the first unit to give an output of 0 if it is not a face, and an output of 1 if it is a face. The second output unit must give a 1 if it is a picture of a woman, and a 0 if it is a picture of a man. In the first instance, all weights are set randomly, and the output will therefore also be random. With a photo of Angelina Jolie, we would like to get the output 1, 1, and with that of Brad Pitt, 1, 0. But in both cases, we will get something like 0.5 and 0.5. We then have to change the weights and see if there is an improvement in the output. It is a long process in which we slowly give the network the weights that yield the
Alright, so that was a cool little video.
starts with building.
And so now, to continue on, connectionism has made significant progress in demonstrating the power of neural networks to master cognitive tasks. One of those examples is the article on the connectionism perspectives of language learning, representation, and processing by Mark F. Joannis and James L. McClellan, in which he talks about auditory work recognition trace model, the non-Haas visual world eye tracking model, reading and pace tense models, which include SM89 and RM86 models, and also deep learning. And so the central component of the article was to develop computational simulations of key phenomena. Three basic assumptions about the nature of mental representation. So basically, number one is knowledge is represented as a pattern of numerical activity across a large set of simple processing units, as we saw in the beginning of the video. And then processing occurs by transformations or patterns of activity across large sets of connections. And then 3, learning occurs together with innate architectural and learning mechanisms plus experience. And so the trace model is basically Mike Cleland's and Ellen Oman who will talk about it. And how does it stimulate word recognition? Well, basically represents auditory, phonemic, and word-specific information. As you can see on the graph, on the figure, you can see that first it starts with the phonemes. That's like, like for example, bat. First you start with the B, and then you start affiliating it with features, as you can see, and then essentially do the whole word. And then continue on. It also talks about the Osseous visual world and also the lexical effects of that can have. And so on the left hand side, you can see the lexical effects, which of the study found that listeners' categorization of an ambiguous phoneme can be biased towards producing familiar words. So what that means, as you can see, like they can give them the first, the last 3 letters of task, and then there could be a bias between deciding if that's going to be the word task or task. And so that also depends on the voice answer time. So that also is in relationship with it. And then as you can see on the right hand side is representing the visual role deniers of eye tracking, basically meaning that the there's a they establish a visual world paradigm in which they either represent and arrive with visual objects as objects to hear words or sentences corresponding to it. And so, as you can see, you know, it also finds eye movement whenever they hear the word. So that's something that I found really interesting. How like as soon as they hear a word or sound, their eyes move, a certain way, and so that was pretty interesting. And also goes back into talking into the phoneme restoration effect, which basically means that is when one of the words phoneme is replaced with white noise. And so basically what this causes is an auditory illusion in which the missing phoneme has been restored. And so basically, why does this happen is that people use top-down information to supplement the imperfect bottom-up sensory information. For example, like the word right here, break, you can, I said break automatically, but there's no R on it. So, the human mind automatically just puts an R on it, just because when, everything's connected, and then the connectionism theory is saying that just because you have those previous experiences and you have those inputs and outputs where you can make that connection that is going to say break and fill in the blanks. And then so we go on to talk about the RM86 and SM89. So basically on the left hand side you can see the RM85 86. And so what that is basically it's a proposed model designed to learn the mapping between verbs present and past tense forms. The model receives an input, which is the present tense, and then has to produce an output, which is the past tense. And then uses a learning algorithm that adjusts connections weight based on experiences with correct past tense forms, just as that the model's performance gradually improve with experience. So with experience, and with different repeating it a bunch of times, then obviously it gets better. It's like a statistical. The more you do it, the better examples, the sample size you have, the more concrete, um, conclusions you can have. And so you can see on the right hand side, that's the SM89, and then its word knowledge is modeled as a confluence of orthography, phonological, and semantic codes. And so you can see, in the figure how like everything is attached to it, everything works together, like meaning goes to orthography and then can only go from there to phonology, and then from phonology it can only go to meaning, or vice versa, from meaning to phonology, and then from phonology to orthography. So, as the difference between those two is that in the RM86 you can have one input and various outputs, but with the SM89 you have one input, one output, and then it could even really, and then the same thing goes backwards. Some critics of the connectionism is the biological possibility of back propagation. And what back propagation is the method the method that calculates the gradient of the error function with respect to the neural network's weight. And so, basically just the error, uh, um, analyzes the error. And so basically saying that there's no biological possibility for us to test that, to have like have it biologically be tested by an algorithm. And so I found that pretty interesting. The stability plasticity of earned representations. Some phenomena require the ability to rapidly learn new information, but other sometimes that those skills needs to be learned. So it's like um it's like a balance of both. And then with connectionism, it says that everything's connected through one channel, or through different channels. But it's just that's one of the critics that it has. And also the spatial and temporal variance, which is the blank spaces, and um, something that can be apparently it come easy to people, but it can be pretty hard for some people, especially some people that have diseases or don't have their brain doesn't work fully. And so this comes into like AI that I will talk about in a couple more slides. And so advantage of connectionism is the multiple realizability. So, there's a lot of realizations that can happen between, the different connections that it has. High tolerance to damage. So, basically, like that's with the time and like different number of times that is done. So high tolerance to damage, the more times you do it, the higher the sample size, the more error, the less error that you have. I mean, so more tolerance to damage, and there's a relationship between syntax and semantics. And so now talking about the connectionism and artificial intelligence. And so can the theory of connectionism work on improving artificial intelligence? What does it prove? And so I went ahead and, there's some research on that. And then I found a model here by Warren McCulloch and Walter Pitts, where it shows the it's an artificial neural network. So kind of basically relates to, like, um, the trace diagram that we saw earlier from the article. And so, the weight or strength of each input is indicated by the relative size of its connection. So as you can see, the neuron N is firing a 4, and an output of 4, and as you can is an output of 4, which is a weight of 4, and it's inactive unless combination with input signals is retrieved from W, X, Y, Z that exceeds 4. So basically all those inputs right here need to exceed 4 in order for this to be active. And so I found that pretty interesting how it actually works with artificial networks and like, with the artificial intelligence. And then to go more into depth, I went into did some research into the Chinese room argument by John Searle, what he compares and proves that connectionism actually doesn't make strong AI, instead it's weak, And so what the Chinese room argument is, where like, they put you in the room and they start, you don't know Chinese, and they start throwing you, little start throwing you Chinese, like, words, and you start taking, so you start stimulating them, and eventually you get so good that you start thinking, and you can actually you actually know what words are word to word. You start like learning Chinese in a way, but that's just just you making connections, of how everything feels, of how how it sounds, how it look, not how it looks, yeah, how it looks, and then everything is with that. And so basically what it's trying to prove is that at the end of the day, you can, if humans can, at the end of the day, you're not really thinking, even humans are not thinking. So if humans are not thinking, then how can machines say he's thinking? If no thinking is done, then it proves that it doesn't have a mind. And so that's a big argument because, as we have learned throughout at the beginning of the class, that, some researchers argued that the, the machines can have a mind of its own. And so I feel like with this Chinese room argument, the Chinese room argument proves that wrong, and indeed it doesn't. It can't have a mind, especially in relation to connectionism. And so I found that pretty interesting because it proves that it can be strong AI is false with the connectionism theory, and I feel like it could be used as like as a test for like for like maybe to like electric cars to prove that that maybe at some point it could get so strong but it will never have a mind of its own. And like you can prove that in machines, it can get to a point where you stimulating it and doing it so much often that you cannot you think you're thinking they're thinking, but it's at the end of the day you're not really thinking, so it can prove that at the end of the day a machine can't have a mind of its own. So I find that pretty interesting, especially what it can do for the future of cognitive science. Maybe this could be used as an example to maybe in the future, when they do like robots and stuff, this could be something that they can look back to and be like, okay, maybe we can grow from this, or we can take this research and maybe prove it wrong with new new advances or or new arguments. And so I find that pretty interesting. And then even though the representation comes from very patterns and are not computed on directly, they result entirely from syntactic manipulations and so cannot be said to model human-like understanding. Again, going back to the point that at the end of the day, this proves that and what the this proves that with connectionism that you can't really have a machine have a mind of its own. connectionisms and bilingual people. So basically, that's another thing that I want to add. That's kind of like my own addition to the research is maybe using connectionism to study how people can can transition better from to from like learning a second language. For like myself, I'm bilingual, so you know it could be. And then when I first came to the U.S., it could be, I had a lot of struggles to learn the new language. So maybe we can use this connectionism to further do research on how people learn from people learn English that do not have English as a first language, and I feel like that could benefit a lot of people that come into the U.S. Whether from be from like all over the world. Maybe we can do more research on that. Maybe we can transition students into school better. Maybe we can help them learn English faster as well. And so it's because because the brain stimulate human data in bilingual reading task. Like nodes connected to patterns of similar like connections, just like the connectionism, you know. And then various models are different on certain architectural details. Some use localist representation. So just how they study bilingual people and connectionism together align. And so I feel like this could help in the future. Um, yeah, so that's it. That's my presentation, and this is my work site, and I hope you enjoy it.